Click the bell icon to get latest videos from Ekeeda.
Hello friends, welcome to finite element methods. In the last class, we have seen how to derive a potential energy expression from a differential equation. So now let us solve that differential equation using the Rayleigh method. A Rayleigh method is nothing but whatever we did in the potential energy approach, the same thing we do. So we will assume a solution and we will substitute that one in our potential energy expression, and we will take the variation of that, the potential energy expression, with respect to the variables, with respect to the constants, and make it to 0. Find out the constants from them and get your solution. So in the last class, we have derived the potential energy expression or the functional for the governing equation u double prime minus u plus x is equal to 0 is pi b equal to half integral u prime square minus 2xu plus u square into dx. This is my pi p. So let us solve this equation using the Rayleigh. That is, according to Rayleigh method, let us assume a trial solution u tilde of x as this solution we have assumed even in the previous class. Sigma I is equal to 1 to 3 ai sine I by x. So let us substitute this one here and take the variation of pi p and make it 0. So that implies what is u tilde is nothing but a1 sine pi x plus a2 sine 2 pi x plus a3 sine 3 pi x. This is the expansion, and that implies u of pi p is nothing but half integral 0 to L u prime square minus 2xu plus u square into dx equal to 0, where this has to be tildes now. These are tildes, trial solutions. So now what is u tilde prime? U tilde prime is nothing but it is pi a1 cos pi x plus 2 pi a2 cos 2 pi x plus 3 pi a3 cos 3 pi x. So just substitute this u tilde prime and square it, and this is also 2x multiplied by u tilde. This is substitute here, and this is also u tilde square. Okay, so upon substituting everything, then what you have to do is you have to take the variation of pi p with respect to ai equal to 0. So if you take this, that is, you will get three simultaneous equations: dou pi p by dou a1 equal to 0. This is the first equation, and dou pi p by dou a2 equal to 0, and dou pi p by dou a3 equal to 0. This is the third expression. So if you substitute all those things, and then you will get a1, a2, a3 individually, calculate them and compare these values. I'm not doing all those things, all those calculations, because it's pretty straightforward. You can use the orthogonality conditions. These are sine, cos. Already I have written some orthogonality conditions. Compare this with Galerkin method. They will be perfect match between these two methods. You will get a1, a2, a3 as same as previous Galerkin method. So now let me write those expressions also. Integral 0 to L sine I pi x by L sine j pi x by L into dx equal to L by 2 if I equal to j equal to 0 if I not equal to j. So you can explore it. You can use this integral directly in the expressions if you want to solve before, because those are squares are there, and it will be easy for you if you use this expression to calculate the thing. So this is one problem. And what is the second problem is, I can use the same Rayleigh approach for calculating the deflection in beam problem. So let us take a beam problem. Let us consider a simply supported beam as, let us take this as my beam, and the same problem what we did earlier, and this is my loading Q and the beam length is L. So now the governing equation for this, or the potential, we are dealing with potentials now. So the potential pi p is given as integral 0 to L half EI V double prime square, the one we derived in the previous class, previous class, dx minus integral QV from 0 to L dx. So this is my pi p. So what I have to do now? I have to assume a solution and substitute here. So let v tilde of x. What v tilde is nothing but a trie solution. V tilde of x is given as sigma I is equal to 1 to 3 ai sine I by x by L. You can take up to 2 terms or 3 terms. Let us take 3 terms. If you take 3 terms, then v tilde of x is nothing but a1 sine pi x by L plus a2 sine 2 pi x by L plus a3 sine plus a3 sine 3 pi x by L. So you are having double derivatives for this, where if you do double derivative, v tilde double prime of x is nothing but, since you have sine, so if you double differentiate it, again the same sign will appear, but with a negative 1 before, minus pi by L whole square a1 sine pi x by L minus 2 pi by L whole square a2 sine 2 pi x by L minus 3 pi by L whole square a3 sine 3 pi x by L. This is v tilde double prime, and now we have to square this one and substitute in our expression, and after that you have to differentiate that one with respect to the constants, that is dou pi t by dou ai equal to 0. That implies how many constants we are having here? 3 constants, a1 a2 and a3. That is dou pi t by dou a1 equal to 0, and dou pi p by dou a2 equal to 0, and dou pi p by dou a3 equal to 0. Since our v tilde equal to sigma I equal to 1 to 3 ai sine I by x by L, and if I differentiate this one, meaning I'm just trying to write in a compact form, that's all. So v tilde prime is nothing but, it is I pi by L sigma I is equal to 1 to 3 ai cos I by x by L, and v tilde double prime is nothing but minus cos for minus, it is I pi by L into I pi by L sigma I is equal to 1 to 3 ai sine I by x by L. Instead of writing all those things in the previous, you can write like this also. This is also fine. Okay. And this I is not an imaginary quantity. Don't multiply this I and say that it's minus 1. Don't do that. This I represents the summation thing. Okay. Don't do that. I by x by L. So what I want to write is, I want to write this one. Dou v tilde double prime by dou ai. Why I want to write this? Because this is given as, I will show you. I pi by L into, you're differentiating this one with respect to ai. So it will be sine I pi x by L. If you differentiate that with respect to a, right? Then it is sine I pi x by L. So if you put I is equal to 1, then it will be dou v tilde double prime by dou a1 is nothing but I equal to 1. It is minus pi by L whole square sine pi x by L. Isn't it the same thing that we did here? So what is this v tilde double prime? It's nothing but minus pi by L whole square a1 sine pi x by L minus 2 pi by L whole square a2 sine 2 pi x by L minus 3 pi by L whole square a3 sine 3 pi x by L. So if you differentiate this one with respect to a1, it will be minus pi by L whole square sine pi x by L. The same thing we got even here, minus pi by L whole square sine pi x by L. It is just like in a more compact form, because if the terms increase, then you can do like this. Then you can segregate, meaning you can divide everything in a more nicer manner. So this is the one. Just remember this. This is the first one. Now dou v tilde double prime by dou a2 equal to minus 2 pi by l whole square sine 2 pi x by l, and dou v tilde double prime by dou a3 equal to minus 3 pi by l whole square sine 3 pi x by l. Let this be 2 and this be 3. Similarly, let's do for dou v tilde by dou a1. That is nothing but, what is dou v tilde by dou a1? It is sine pi x by l. Dou v tilde by dou a2 is nothing but sine 2 pi x by l, and dou v tilde by dou a3 is nothing but sine 3 pi x by l. So keeping these things in our mind, let this be 4, this be 5, and this be 6. What we want to do is, we want to differentiate this pi p. Dou pi p by dou ai equal to 0. That implies, what is our pi p? Pi p is nothing but half integral ei v double prime square dx minus integral qv dx, where the limits are from 0 to L. Now this is dou pi p by dou ai equal to half integral 0 to L ei. This will be dou by dou ai of v double prime square dx minus integral 0 to L q dou v by, this has to be v tilde, don't confuse. This is the approximate solution. Dou v tilde by dou ai into dx. So now we are having our v tilde, square that one, then differentiate that one with respect to ai. Then you will get these expressions. Already we did this, dou v tilde by dou ai. We did for v tilde double prime, not v tilde double prime square, but do it for v tilde double prime square. Then substitute here. Then, meaning I have shown you a compact form, right? Just use that compact form and differentiate this v tilde double prime square with respect to ai. So substitute it here. Then you will get, that is, if you differentiate with respect to a1, then you will get a1 as 0.0130711 q l power 4 by ei, which is the same thing we got in a Galerkin's method, as well as a2 equal to 0 and a3 is equal to 0.0000538 q l power 4 by ei. This is a3. So our final solution will be the summation of the linear combination of a1, a2, a3. Okay. So our v tilde of x is nothing but a1 f1 plus a2 f2 plus a3 f3, where I meant f1 f2 f3 are sine I by x by l's. There is sine pi x by l, sine 2 pi x by l, sine 3 pi x by l. So if you compare these values with our previous Galerkin method, both are exactly same. There is not much variation at all. So that means that this Ekeeda's method, as well, that is the potential energy approach, as well as the Galerkin method, they both give the solution of same accuracy. So that's why you can do any method and you can get the solutions very accurate using these two techniques. And so we are going slowly into the FEM, the actual FEM. We will apply these Galerkin methods element by element. Meaning, I will tell you, I will define everything. I will define what is an element, I will define what is a node, what is discretization, all the terminology. But anyway, so this is like the precursor to the finite element method. So these methods we will generalize to the finite element method. Then we will solve these methods for element by element, and then we will get the solutions using these methods. Basically, Galerkin and the potential energy are like the forms the basis for the finite element methods. Okay, so you can approach any method. Any method is. Thank you so much for watching this video. Stay tuned to Ekeeda, subscribe to Ekeeda.